Hello everyone, welcome back to our channel. In today's session, we'll explore how to leverage Terraform to automate the creation of Amazon EKS cluster. So we will learn how we can create AWS EKS cluster using Terraform, which will enable efficient deployment and management of Kubernetes workloads on AWS infrastructure. So you can refer the article which is available on fasttechniques.com. So these are the table of contents which you are going to learn today. So there are some prerequisites you should need to follow. So before beginning to practically, you need to follow these prerequisites. So it simply suggests an AWS account with an IAM user. Then you should have AWS CLI installed. Then you should have Visual Studio Code or any other text editor where we can save our Terraform file. And then at last you need to install and set up the kubectl. So currently I'm using Windows. So you should have installed the kubectl on Windows. And if you click on this, I have provided the link of installation of kubectl on Windows. Then we will learn about the Terraform and Amazon EKS. So what is EKS? What is Terraform? And then we will follow with the steps to set up Amazon EKS cluster using Terraform. So which include steps like to create provider.tf file to create VPC, internet gateway, etc. So let's start. So what is Terraform? So it is an open source infrastructure as a code software tool where you define and create resources using providers in the declarative configuration language, example JSON. So with Terraform, you can package and reuse the code in the form of module. It supports a number of cloud infrastructure providers such as AWS, Azure, Google Cloud Platform, IBM Cloud, and etc. Now let's learn about Amazon EKS, which is called as Amazon Elastic Kubernetes Service. So it is a managed Kubernetes service provided by Amazon Web Services. So it simplifies the process of deploying, managing, and scaling containerized application using Kubernetes on AWS infrastructure. So with EKS, user can leverage the power of Kubernetes without complexity of managing the underlying infrastructure. So EKS handle tasks such as cluster provisioning, upgrades, and scaling, and allowing developers to focus on building and deploying applications. So for example, imagine a software development team which wants to deploy microservices based application using container. So instead of managing Kubernetes cluster themselves, they can use the service Amazon EKS. So in which they will define the application architecture, specify resource requirements, and deploy it to the EKS cluster. So basically, Amazon EKS takes care of provisioning and managing the Kubernetes control plane, worker node, networking, and other infrastructure components. So this will allow the team to focus on developing the application while benefiting from the scalability, reliability, and flexibility of Kubernetes on AWS. So basically, to create a Kubernetes cluster in AWS, there are several AWS resources you should be with familiar, which are required to be provisioned. So the resources which need to create a Kubernetes cluster on AWS are like Amazon Virtual Private Cloud, which is called as VPC. So basically a VPC is a logically isolated section of the AWS cloud where you can launch AWS resources in a virtual network. So it's recommended to create a VPC specifically for your EKS cluster to isolate its networking from other resources. So Terraform's AWS VPC resource can be used to define and create a VPC. Then comes the subnets. So subnets are segment of VPC IP address range where you can place AWS resources. So EKS requires at least two subnets across differently availability zone for high availability. So it requires at least two subnets. So Terraform AWS subnet resource can be used to define and create subnet within the VPC. Next resource is the Internet Gateway. So an Internet Gateway allows resources within the VPC to communicate with the Internet. So it's necessary for resource within the VPC including case worker nodes to access external resources. So Terraform's AWS Internet Gateway resource can be used to create an Internet Gateway and attach it to the VPC. Then comes the route tables. So route tables defines how traffic is routed between subnets and the Internet Gateway. So you'll need to create and associate route tables with the subnet to enable internet access. So Terraform's AWS route table and AWS route resources can be used to create and define routes within the route tables. Then comes the security groups. So security groups basically act as a virtual firewall that control inbound and outbound traffic, for instance. So you'll need to create security groups for EKS, control plane, and workflow. So Terraform's AWS security group resource can be used to define and create security. Then comes the IAM rules and policies. So IAM rules and policies define permission for resources to interact with other AWS services securely. So we need to create an IAM rule for the EKS cluster and attach necessary policies for EKS management. So Terraform's AWS IAM rule and policy attachment resources can be used to define the rules and attach policies. Then finally comes the Amazon EKS cluster. So the EKS cluster is managed Kubernetes control plane provided by AWS. So Terraform AWS EKS cluster resource can be used to create an EKS cluster. So we need to specify the VPC and subnets where the EKS cluster will be deployed. Then finally comes the node groups, which is optional. But in today's session, we are going to create node groups. So node groups are the groups of EC2 instances that serve as worker node in the EKS cluster. So you can create node groups to scale and manage the compute capacity of our cluster. Terraform's AWS EKS node group resource can be used to define and create the node group. Now, moving on forward, now we will see steps to set up the Amazon EKS cluster using Terraform. So if you click on this, you can get the required code where you can create AWS EKS cluster on your AWS account. So let's begin with the practical. So first, I have created folder called as AWS EKS cluster, and in that folder, the first file I'm going to create is of provider.tf file. So just type a provider.tf file and press enter. Now, so the provider.tf file in Terraform, which is a configuration file that will specify cloud provider and its corresponding plugin that Terraform will use to manage resources in that provider. So just copy this and paste it in the editor and save this. So as you can see, this is just the provider block where I have mentioned the provider and I am currently using AWS as provider and I am currently using the region AP South 1 and the profile is set to default where I have specified my access key and secret key. Then is the Terraform required provider where this block configure Terraform setting for the entire configuration directory. So it will allow you to specify global settings for Terraform. And in required providers, here you can find So it will specify the provider that Terraform needs to interact with to manage resources. So here you can find the version is 3.0. So this line will specify that the version constraint for the AWS provider, and the operator specifies a version that it only accepts minor and patch version greater than or equal to 3.0. So overall, this configuration sets up Terraform to use the AWS provider to manage resources in the AP South 1 region using the AWS credential profile named as default. So it also specifies the Terraform configuration requires the AWS provider with a version of at least 3.0 but less than 4.0. Now move on to forward. Next we are going to create a VPC. So as per the requirement to create a AWS EKS cluster, we are moving forward. So our next step will be to create virtual private cloud in AWS. So this step, we will create a virtual private cloud in AWS using the resource called as AWS VPC. So you can also refer Terraform registry and type their AWS VPC resource and you can find the code. So now there is one required field that you need to provide, which is the size for your network. So that will give you approximately 65,000 IP address. So I am using this CIDR block, which is 10.0.0/60. So let's make a file called as vpc.tf file. So now we are going to create VPC and here just copy the code and paste it in the editor and save this file. So here you can find that resource AWS VPC and we are going to give the VPC name as AWS EKS VPC name. And then the CIDR block is set to 10.0.0/60. So this line will specify for the CIDR classless inter domain routing block for the VPC. So the CIDR block will define the IP address range that the VPC will encounter. So in this case, it's set to this and which will allow up to 65,536 IP address within the VPC. And the tag name I have given for the VPC is AWS EKS VPC. So we have successfully created VPC. So our next file to create an internet gateway in AWS. So in order to enable internet connectivity for our services, it's essential to incorporate an internet gateway within our VPC infrastructure. So now we will create file called as internet gateway and paste the internet gateway code. So we are going to use the resource called as internet gateway to create an internet gateway. So as you can see, so this Terraform configuration creates an AWS internet gateway and associated with the specified VPC. Here you can find the VPC name which we have earlier created called as AWS EKS VPC.id. So the internet gateway, after creating an internet gateway, it will allow traffic to flow in and out to the VPC. So basically it will enable the communication between the resources within the VPC. Now next, we are going to create the private and the public subnet in AWS using Terraform. So we will proceed to create 4 subnets adhering to EKS guidelines. So we are required to publish 2 public and 2 private subnets across the distinct availability zones. So now let's name our subnet file as subnets.tf file and press enter. Now copy the code where we are going to create two public and two private sub. So here you can find that first resource I have created a private subnet and the cider block is set to 10.0.0/19 and I am going to create the private subnet in the AP South 1 A availability zone. Then I have given some tag name. Then I have given some tag name as private AP South 1A. Then I have created another subnet, private subnet in the 1B availability zone and with the required cider block in the availability zone and the tags for the private subnet. Then if you come down, then I have created a public subnet in the availability zone AP South 1A with the required cider block and you need to mention the VPC ID here. So as we have created the VPC here, AWS EKS VPC name, you should need to specify the VPC ID here so that it can create the subnet, required subnet in that VPC only. Then again, I have created an public subnet in the AP South 1 viability zone with the required hidden block and the VPC ID and given the tag name for the another public subnet as public AP South 1B subnet. So overall, this configuration will set up network topology suitable for AWS EKS cluster with private and public subnet distributed across multiple availability zones for high availability and redundancy. And the tags assigned to subnet help identify the purpose. Now next we will move on forward and create a NAT gateway in AWS using Terraform. So let's now set up a NAT gateway essential for private subnet connectivity to the internet. So to begin, so we need to allocate a public IP address. Subsequently, we need to utilize it within the AWS NAT gateway resource. So placing it with the designated public subnet, which must have an internet gateway as the default route. So now we are going to create a file called as NAT gateway. And if you press enter, then copy the code. So first to create a NAT gateway, we have so after entering your code here, save your file. So first you are going to create a resource called as AWS EIP, which means that this resource block will define the configuration for creating an elastic IP address. And the tag name which I have given is NAT. So basically this block will define tag to the elastic IP. So the tags are key value pair used for identifying and organizing AWS resources. So in this case, a single tag with the key name and the value NAT is assigned to the elastic IP, providing a human readable name for the resource. Next resource, as we are going to create a NAT gateway, so the resource name is AWS NAT gateway, and the name for the NAT gateway I have given it as NAT. And then you can find the allocated ID, so which will basically specify the allocation ID of the elastic IP address associated with the NAT gateway. Then you can find that subnet ID as subnet ID is given as public AP South 1A. So This line will specify the subnet ID where the NAT gateway will be created. And it uses the reference AWS public AP South 1 ID to retrieve the ID of the public subnet where NAT gateway will be reset. And the tag have been given as NAT. And then you can find that it is depend on the internet gateway. So basically, to depend on line, we specify that creation of the NAT gateway depends on the existence of the internet gateway. So the NAT gateway needs the internet gateway to be attached to the VPC before it can function properly. So basically, overall, this configuration sets up an AWS NAT gateway and associates it with an elastic IP for outbound internet traffic from instances in private subnets within the VPC. Now moving on forward, now we are going to create a routing tables and associate subnets in AWS using Terraform. So by now we have created subnet, the internet gateway and NAT gateway. So now it's time to create routing tables and associate subnets with them. So simply we will create routes.tf file where it will consider our route table and associate sub. So simply copy this code and paste in the editor. So here you can find the resource as we need to create a route table. The resource route AWS route table have been used and the private. So basically the entire block will define a route table which I have given the name as private. So for private subnets and it will specify the VPC ID to associate route table with and adds a route for all traffic. Here you can find in the header block to go through the NAT gateway. Here I have mentioned the NAT gateway ID. And so the NAT gateway provides internet access for resources in the private subnet. So tags are assigned to identify the route table. And these are the required other parameters we need to create. So these parameters will be filled after we apply our configuration. So the first route table I have given the tag name as private as it is for the private. Next, I have created the route table for the public and you should specify the VPC ID. So it will create the route tables specifically for that VPC. So the VPC name is AWS EKS. So now, next we are going to create a route table for the public. So basically, this line of block from resource to the end of the tag name will define a route table named as public for public sub. So it specifies the VPC ID and adds a route for all traffic to go through the internet gateway. And the internet gateway provides the internet access for the resources in the public sub. So tags are assigned to identify the route table. So I have given the name as public. So all other parameters are required, but it will give the information only after the Terraform compile. Next, I am going to create a resource for the route table association. So I am going to create a route table association for the private and the public subnet. So you just need to mention your subnet ID for the private subnet and the subnet ID for the public subnet and the route table ID which we have created earlier. According to that, we are going to create a route table association for public and private subnet. So similar association are made for the subnets. So this association ensures that each subnet has the appropriate routing setup for internet access and other network traffic based on their intended use, so public or private. Now our next step after we have successfully creating the route table and associate subnets in AWS. Now our next step is to create an EKS cluster. So before setting up EKS cluster, so we need to establish an IMI role named as EKS.tf with Amazon EKS cluster policy. So to enable Kubernetes cluster to manage AWS resources autonomously. So now we are going to create an EKS. So just enter the EKS.tf file and then copy the resource. So now we are going to create an IAM role. So to create an IAM role, we have to take the resource name as AWS IAM role and the name for that is EKS. So as you can see, so this whole block resource IAM role will create an IAM role named as EKS cluster EKS that will allow the Amazon EKS service to assume this role. And the assume role policy specifies the trust relationship between the here you can find the role policy that will grant the Amazon EKS service permission to assume the role. So as you can see, the block will create an IAM role named as EKS cluster EKS and that will allow Amazon EKS service to assume the role. And the assume policy here you can find the assume policy specify the trust relationship policy that will grant the Amazon EKS service permission to assign this role. Next, we are going to create an role policy attachment and I have given the name for that is EKS Amazon EKS cluster policy. So basically, this block will define the Amazon EKS cluster named EKS cluster and it will specify the role IAM role that will grant the permission to manage the EKS cluster and the VPC config block here and the VPC config block will specify the subnet ID where the EKS cluster will be deployed and the depends on here you can find the depends on will ensure the creation of the EKS cluster depends on the attachment of the IAM policy which we have created earlier. So this the end block will specify the cluster and the name of the cluster is EKS cluster and here you need to specify the role which we have created and as well as the role policy attached to it is depend on the role policy attached and here you need to simply in VPC configs you need to specify a subnet ID such as for private here you can find the specific ID is private AP South 1A and private AP South 1B same as for public sub. Now next we will create a single instance group for Kubernetes. So now next, our next step is to create single instance group for Kubernetes. So we'll establish a single instance group for Kubernetes, which is like EKS cluster, necessities, and IAM group. So now we're going to create a node group. So simply create a folder, file called as node.tf. And in this, just copy this code and we will break down. Save the EKS.tf file as well as the nodes.tf file. This Terraform code will set up the AWS EKS Elastic Kubernetes Service node group along with the necessary identity and access management roles and the policy. So here you can find the resource called as IAM role, and you need to create a role for the node. So this block will create an IAM role named as EKS node group nodes that will allow EC2 instance to assume this role. And the assume policy, role policy will specify the trust relationship policy that will grant EC2 instances permission to assume this role. Then you can find the IAM role policy attachment. So the resource for this is IAM role policy attachment, and the name is node Amazon EKS worker node policy. So basically, this will create a worker node policy that will be managed by IAM policy to the IAM role created for the AKS node group. So these are the IAM role policy attachment for the node groups. Then we are going to create a block called as AWS EKS node group, where we are going to create a private node. So basically, this block will define the AWS EKS node group named as private nodes, and it will specify the cluster name, which is AWS cluster.eks cluster.name. Then it will specify the IAM role ARN for the node, the subnet IDs where the nodes will be launched. Here you can find the subnet IDs and where the and the instance type. Here you can find the capacity of which is on demand, and the instance types is t2.micro. And then we come to the scaling configuration for the node group. So its desired size is set to 1 and max size is set to 5 and minimum size is 0. Then you can find it depends on parameter where it will ensure that creation of the node group will depend on the IAM policy being attached to the IAM role first. So here you have created an IAM role policy attachment. So it is depend on that. So you just need to specify this in the depends on block. So overall, this configuration will set up an AWS EKS node group with necessary IAM roles and policies to manage the node instances securely within the Kubernetes cluster. Now our next step will be to create IAM OIDC provider EKS using Terraform. So to manage permission for your application that you need to deploy Kubernetes. So either we can attach policies to the Kubernetes node directly. So in that case, every pod will get the same access to the AWS resource. Or we can create an OpenID Connect provider, so which can allow granting IAM permission based on the service account used by the pod. So now we are going to create a file named as im-oidc.tf. And in this, just copy this code. So here you can find that this block is using an TLS certificate data source to fetch the information about an TLS certificate. So in this case, here you can find it is fetching the information about the certificate used by the OIDC, which is OpenID Connect provider associated with the EKS cluster. So basically, the URL line will retrieve the OIDC issuer associated with the EKS cluster, and the AWS EKS cluster resource will define the EKS cluster, and we are accessing its OIDC issuer URL through the identity attribute. Next, we are going to create a resource called as AWS IAM OpenID Connect Provider, and the name is EKS, where we have to specify the parameters like client ID, system list, and URL for the TLS certificate. So as you can see, this block will define an OpenID Connect provider in IAM, so which will correspond to the issuer for the EKS cluster. So as you can see, the client ID list will specify the list of client ID that are allowed to authenticate against the OIDC provider. And here only the sts.amazonaws.com is allowed, which is the AWS security token service. Then is the thumbprint list. So basically, the thumbprint list will specify the SHA-1 fingerprint of the certificate associated with the OIDC provider. So it will fetches the SHA-1 fingerprint from the TLS certificate and the data fetched earlier. So this thumbprint ensures that the certificate is trusted. Then comes the URL, which is set to the cluster name and the identity and the issuer. So here you can find the URL. So it will be associated with the EKS cluster similar to what it is specified to the data TLS certificate. So overall, this configuration will set up an IAM OpenID Connect provider in AWS. So it will ensure that OIDC issuer associated with the EKS cluster is trusted and allows authentication for the AWS security token service, which is the sts.amazonaws.com. Now our next step is to test the provider first before the deploy. So I highly recommend that testing the provider first before deploying the autoscaler can save a lot of time. So to save the time, we need to create a file called as imtest.tf, and here you need to just copy this code and paste it and save this. So as you can see, I have created the AWS IAM policy document and specified the name as test over OIDC assume role policy, where it has the required parameters. So basically, this Terraform configuration will set up an IAM role and associated policies for managing access permission within the Kubernetes cluster likely running on AWS EKS Elastic Kubernetes Service. So as you can see, the data AWS IAM policy document will specify the block that allows assuming a old role using web identity, which is OIDC, and it will set the permission based on the specific condition, such as actions, effect, test, variable, values, identifier. So action will specify the action allowed, which is assuming a role with the identity, and the effect is set to allow, which indicate that defined actions are allowed. Then comes the condition block. So it will specify conditions under which the action is allowed, under which the test is set to string equal, which define the condition test which checks if the provider strings are equal. Then is the variable, which will specify the condition variable, which in this case is the subject sub obtained from the OIDC provider URL. Then is the values, which is the list that the values that condition variable should match. Then is the principal block where you need to define the entities that are allowed to assume the role. So that type is federated, which indicates that the entity is federated user of application. Next, we are going to create an IAM role for the test OIDC. Then we will create an assume role policy, and the name which I have given for this role is test-OIDC. So basically this block will create an IAM role and it will set the assume role policy to the previously defined IAM role IAM policy document. Next block, I have creating a IAM role policy named as test policy that will define the permission for accessing the S3 resources. So the name I have given as test policy, which will specify the name of the IAM policy, and the policy will define the permission allowed by the policy, in this case listing buckets and getting the bucket location. Then comes the version and effect and resource. So finally, the next block will define an IAM role policy attachment for the test. So which I have given the name as test attach. So it will specify the role of the IAM to attach the policy and the policy ARN, which will specify the ARN of the IAM policy to attach. Next, I have taken as output test policy ARN. So this will give an output variable named as test policy ARN, which will give output of the ARN of the IAM role created. Now next, we'll move on to forward and at last we will enhance our Kubernetes cluster with the add-ons. So before that, so basically this configuration, the policy document is significant for Kubernetes cluster as because it sets up an IAM roles and policies to control access to resources within the cluster. So by defining the role policy, it will ensure that only authenticated entities with specific conditions through the OIDC provider can assume the role. Now, next step is to enhance a Kubernetes cluster with the add-ons. So let's understand about the add-ons. So the Terraform, we are going to use three add-ons for the Kubernetes cluster, which is core DNS, the kube proxy, and AWS VPC CNI. So basically, core DNS is a flexible and extensible DNS server that is used as the default DNS server in Kubernetes cluster. So basically, it will resolve DNS queries within the cluster and provides service discovery functionality. Next is the kube proxy. So basically, kube proxy is a network proxy that runs on each node in the Kubernetes cluster, and it will maintain network rules on nodes and performs connection forwarding and load balancing across the cluster. There comes the Amazon VPC CNI add-on. So it's the container network interface. So it is a plugin which allows Kubernetes pods to use AWS VPC networking for networking between pods. So it will assign AWS Elastic Network Interface to pods, allowing them to communicate over the VPC network. So these are the uses of the add-ons. So by defining this add-on, the Terraform configuration will ensure that necessary components for networking, service discovery, and pod communication are provisioned and configured correctly within the Kubernetes cluster. So because of this, it will facilitate smooth operation of application and services deployed on that cluster. So now we are going to create an add-ons.tf file and press enter. And here simply copy the code which will create an add-on for core DNS, for kube proxy, and VPC CL. So we have seen the uses of this add-on. So it's simple, just use. You can also use Terraform registry. So if you copy this resource name and search for this add-on, you can get in AWS EKS add-on, you can get the name. So for example, here you can find the code. So the required code for add-on, and you can directly copy and paste here. So, but just you need to specify the cluster name here and the name of the add-on. Now we will move on forward, and now we will initiate with the Terraform command to apply our configuration on AWS in AWS. So let's start. So just open an integrated terminal. So first command, just type Terraform in it, which will initialize a new or existing Terraform configuration. So as you can see, it has been successfully initialized. So this command will download the required provider plugins and set up the backend for storing state. Now just type Terraform plan. So the Terraform plan command is used to create an execution plan for the Terraform config. So this command will show that what resources Terraform will create, modify, delete, or when apply. So here you can find 29 to add, 0 to change, and 0 to destroy. And I have taken an output as test policy, so it will be known after the apply. And here you can find in the VPC, I've told that all the parameters which are set in the routes which are will be known after the we apply the configuration. Now next, finally we will apply this configuration and check on the AWS console. So just type Terraform apply auto approve. So basically the Terraform apply command will the spelling for. So this will apply all our configuration in our AWS. So as you can see, all the resources has been in creating state. So it will take around 5 to 7 minutes to create a cluster in our AWS. So let's wait. So now we have successfully applied. So now we will check the resources are created in our AWS or not. So just visit your AWS account, and here you can find I have searched Amazon Elastic Kubernetes service in the search, and if you click on the clusters, here you can find that a cluster has been created successfully, and the current version of Kubernetes is 1.2. So if you click on this, here you can find the overview details where when a cluster is created, the OpenID connect provider URL, the certificate, and etc. The server endpoint and etc. And in networking, here you can find the VPC and two public and two private subnet we have created successfully. And in compute, here you can find we have created the private node successfully. So let's check the private nodes first. So just type here EC2, click on EC2. Here you can find two instances. So if you the one instance is of Grafana, and here if you click on the other instance, here you can find that this is the So here you can see the instance type we have created as T2 micro and the VPC ID. So this is a private node. So again, if you go back in the Elastic Kubernetes service, select the cluster. Now we will check for, after checking the networking here, you can find the security group, etc. Now we will check on add-on. So as you can see, the add-on has been added successfully. So the status for core DNS is degraded as it is still in process. Here you can find it is still in creating state. But the other resources have been created successfully and the status has been in active. Here you can find the workload pods. There are four which are created. Then 7 minutes the node core DNS 10 minutes up and the queue proxy. Now we will export the Kubernetes context. So we can use the AWS EKS command in the command. So now we will move on to the next step. So just copy this command and paste in the command prompt. So before that, as we have followed with the prerequisites, you need to install AWS CLI and then you need to configure with your access key and private key. So I have done that step. So we'll move on to forward and type the AWS EKS region, and the region is AP South 1, and it will update the kube configuration file of kubectl, which will specify the name of the cluster, which is EKS cluster. So if you enter this, here you can see it has updated the context. So kubectl should be installed. So you can see I have already installed, and you can check with the kubectl version. So here you can find the version name, the version 1.29.2. So I've mentioned the link to install the kubectl as well as AWS CLI. You can follow that from prerequisite. Now our next step is to check the connection of EKS cluster. So we will check the connection by simply typing kubectl get svc. So here you can find our name, the type, the ports, and the age. And if you type kubectl get nodes, it will give the information of the node. So here you can find the nodes which you have created as private. Then the status is ready and it's also with the version. So basically kubectl get svc is a command in Kubernetes to retrieve information about the services within a cluster. So after typing, we have fetch a list of services in the current namespace by default or across all the namespace specified. Now, this information is useful for managing and monitoring the services running in Kubernetes cluster, which will allow administrator and developer to understand how the services are exposed and accessible within the cluster. So we use the command kubectl command. So we have successfully created an EKS cluster in AWS using Terraform. So we will conclude for today. So in conclusion, and make sure that after you have created all the resources, just type your in enter in command prompt, just type a Terraform destroy, so it will destroy all the resources. So it is still creating the core DNS. So now we will just execution. We will hold the execution as we have successfully added the episode VPC, and this is for just a demo. So now we will type your Terraform destroy command to destroy all the resources. So it will take around 5 to 7 minutes to destroy all the resources. So as you can see, it is refreshing the state and it will destroy all the resources created in AWS. So let's conclude for today. So in conclusion, using Terraform to create Amazon EKS Cluster streamlines infrastructure provision, forecasting, efficient deployment, and management of Kubernetes workload on AWS. So because of Terraform, it will leverage the capabilities. Users can establish consistent and scalable Kubernetes environment tailored to their specific needs, ensuring reliability and flexibility in their cloud deployment. So thank you for watching the video, and you can refer the article which is available on Post Techniques for the code to create the cluster in AWS. So thank you for watching the video, and please do like and share the video and also subscribe our channel. So see you in the next. Thank you.